Having considered the mechanism of ATP hydrolysis, we now turn our attention to the other important reaction involving phosphate esters in biochemistry, namely the formation of phosphodiester bonds in the synthesis of DNA and RNA. So with the diagram posted on the left here, you can see that nucleotides in DNA and RNA are linked together by these linkages that are called phosphodiester bonds. In other words, the phosphorus is participating in two ester linkages. And the way you can see this is if you look at the phosphorus atom in the center of the diagram and look upwards from it, you see the phosphorus bound to an oxygen bound to a carbon. Therefore, that is one phosphorus ester. And then if you look downwards, you'll see the phosphorus bound to an oxygen bound to another carbon. So that is a second phosphorus ester. So the formation of this phosphodiester bond turns out to be a transesterification reaction with the 3' hydroxyl group on the first nucleotide as the nucleophile acting on the 5' triphosphate, and pyrophosphate turns out to be the leaving group. Okay, so let's look at the reaction scheme here. So on the left here I have depicted the growing DNA chain. So R on the very left of this diagram is everything, all of the DNA nucleotides up until this point. So it is linked to an adenosine, which is the last nucleotide that is part of the chain that already exists, the one that has most recently been incorporated. So what we're going to do is we're going to add a thymidine to the chain so that we can add that to be the last nucleotide in the chain. So the incoming nucleotide, the thymidine, is going to come in as its triphosphate on the 5' carbon. And what happens is the adenosine uses its 3' hydroxyl to attack the 5' phosphate. We'll look at the mechanism in more detail on the next slide, but it's going to attack what's called the alpha phosphorus, the first one closest to the ring, and then the other two phosphoruses are being kicked out as pyrophosphate. Pyrophosphate has 2 phosphoruses, 7 oxygens, and 4 negative charges on it at physiological pH. And pyrophosphate is nature's preferred leaving group. Okay, before we look at the mechanism, I want to go over a couple of notes about this. First of all, this reaction does not take place spontaneously. It requires enzymatic catalysis, and there are many enzymes that catalyze this reaction. So if you're trying to make a DNA chain, it could be catalyzed by DNA polymerase. If you're trying to synthesize RNA from a DNA template, it can be made with RNA polymerase. Or for ligating together DNA fragments, whether it's in DNA replication or DNA repair, this reaction can be catalyzed by DNA ligase. And then finally, a note on this numbering scheme. I've talked about the 3' and 5' positions. Those are positions, they're specifically carbon numbers along the ribose ring, or the deoxyribose ring, if it is DNA. So the 1' position is the carbon that's part of the sugar that is attached to the nitrogenous base, so to the adenine or the thymine. So if you just work your way down the carbon chain, 1', 2', 3' is where there's an OH in the A, and then 4', 5' has the phosphate on it. The reason why we have to use primes is that the adenine and the thymine rings themselves have an independent numbering scheme, and those are the numbers without primes. Okay, so let's look at this mechanism. And again, because it's in this unit on acyl transfer, it's going to be an acyl transfer mechanism of sorts, right? but at least it's going to be nucleophilic addition followed by elimination at the alpha phosphorus of the triphosphate. So step one of this mechanism is that the 3' hydroxyl group is on the existing DNA chain is going to attack the alpha phosphorus of thymidine triphosphate, and that will generate the trigonal bipyramidal intermediate. Remember that the trigonal bipyramidal intermediate on a phosphorus ester is equivalent to the tetrahedral intermediate on a carbon ester. It's just because phosphorus is forming 5 bonds instead of 4 bonds, the geometry is trigonal bipyramidal. Step 2 then is that a basic amino acid on the enzyme, that the basic amino acids are ones that are going to be negatively charged at physiological pH, so that's probably going to be an aspartate or a glutamate. Basic amino acid will deprotonate the cationic oxygen. Okay, so after the 3' OH came in and attacked, it's a neutral nucleophile. So when a neutral nucleophile attacks something, it has not yet lost its hydrogen. So that hydrogen has to be taken off by something because the final phosphodiester bond doesn't have it there, and what takes it off is a negatively charged amino acid residue. Then finally, the last step is going to be reforming the PO double bond. So we take an oxygen that has a negative charge, use it to reform the PO double bond, and obviously we have to kick something out or else we're going to have too many electrons around phosphorus. So we're going to kick out pyrophosphate as a leaving group. And there you have it. After that, you've added your next nucleotide onto your growing DNA chain, and then it's just going to keep going on and on and on and doing the same thing over and over again until you have a DNA chain as long as you want.